Many thanks for giving me the opportunity to give this introduction talk to what promises to be a very exciting session on volcanism in the East African Rift. This is a review talk and therefore I have not formally included any co-authors in this presentation, but of course I do wish to acknowledge the many people that have facilitated and contributed to the work that many of us, including myself, have been doing in East Africa over the years. There are too many to name everybody here, but if you are in the audience, I'm sure you know who you are. So I will talk you through a few aspects of what I think of as typical rift volcanism that we find in at least some places in East Africa, not everywhere, and I will highlight some new findings from recent work. This map shows a structure of the East African rift system in relation to its volcanoes that are thought to still be active and which are taken up in the Global Volcanism Programme's list of Holocene volcanoes. The most obvious expressions of the rift run from the north in the Afar Triangle through the main Ethiopian rift and the Kenyan rift into the North Tanzanian divergence zone. Together, this is what we call the eastern branch of the rift, and it is characterized by a nearly continuous chain of volcanoes. This eastern branch is considered to be a relatively mature continental rift, clearly magma-assisted, and in which a significant proportion of the extensional strain is accommodated aseismically by regular magmatic intrusions. Then we have what we call the western branch of the rift, which is much less magma-assisted, and is characterized by steep border faults and discrete zones of magmatism, which occur in structural accommodation zones, which we also call volcanic provinces. The Virunga volcanic province in the east of Congo and the Rungwe volcanic province in southern Tanzania are the volumetrically most important of these. Altogether, there are roughly 100 volcanoes, active volcanoes, that are recognized in East Africa, and this means that they have either historically erupted, which is the case for about a quarter of them, or that we have indications that they have at least been active in the Holocene. Finally, you also have some encircled areas highlighted, which indicate places where we find abundant andosols that are developed onto young volcanic deposits and which are, together with a favorable climate and the abundance of lakes, often very good conditions for cash crop farming. They only provide one example of the plenty of resources that are associated with the volcanism in the East African Rift. A lot of resources obviously also means a lot of people. So in most places, except perhaps in Afar or in northern Kenya, we have a high population exposure and a total estimated 25 million people living within 30 kilometers of any of the potentially active volcanoes. Volcanic rocks erupted along the East African Rift are invariably rich in alkali elements. This plot shows a total alkali versus silica diagram of whole rock compositions that were retrieved from the GeoRock database. We see that overall in Afar and the main Ethiopian rift, the symbols in blue, compositions are very similar, with two large modes, one near the basalt end and another near the trachyte and rhyolite end. These are per-alkaline rhyolites and represent the most chemically evolved compositions that we find along the rift. In the Kenyan rift, in the green and yellow symbols, and the western branch, gray and orange, we find an overall more alkaline series and typically silica undersaturated rocks that span a compositional range between basanites, alkali basalts, and trachytes and phonolites on the other end. There are some data in the phoidite fields, but they all belong to very specific and rather unusual volcanoes such as Nyiragongo in Virunga and Oldonyolenga in north of Tanzania. The composition is important because the high alkali contents of the magmas reduce their viscosity relative to their calc-alkaline counterparts for a given temperature and volatile content. This plot shows anhydrous viscosity versus reciprocal temperature for different compositions. We see that overall the per-alkaline rhyolite magmas have viscosities that are roughly 2 orders of magnitude lower than normal rhyolites, and that together with phonolites and trachytes, they have viscosity that is relatively comparable to dacite magmas. So it's important to note that we're not dealing with low viscosity magmas as such, which is sometimes mentioned in the literature, but definitely lower compared to what we might expect if we were to consider primarily silica content. But of course, we also need to consider the volatiles. These two plots are from a recent paper by Fiona Idden and Marie Edmonds, in which they analyzed the melt inclusions in olivine, plot on the top, and quartz at the bottom for several main Ethiopian rift volcanoes. They plotted them together with the corresponding storage pressures that they record. We see that overall the rift magmas are relatively rich in volatiles, with up to several thousands of ppm of CO2 and 1 to 1.5% of water in basaltic melts, and often up to 6 or 7, even up to 8 weight% of water in the rhyolite melts. So when we look at the main Ethiopian rift, the map on the left, we see that it's dotted all along by large silicic calderas, indicated by the dark blue lines, and discrete areas of cone fields erupting basaltic melts, which are clearly fault controlled. The wealth of chemical and petrological data that has been collected recently has led to a general model of the plumbing systems along the rift, which is well illustrated by this figure on the right. Importantly, this figure is also broadly consistent with constraints from geophysical observations. It is thought that mafic melts saturated in water and CO2 may directly feed off-axis volcanic cone fields that occur in many rift segments. More central to the rift, these mafic melts rise to depths of 5 to 8 kilometers, where they fractionate extensively to highly silicic and volatile-rich magmas. These shallow reservoirs are mush-dominated with discrete pockets of residual rhyolite melt and can also develop a volatile-rich cap. These exhaust volatiles may interact with active hydrothermal systems that in some places are tapped for their geothermal resources. The chemical composition and rheology of the magmas and the architecture of the reservoirs are of course also important to understand and to interpret the signals of unrest that are detected at many rift volcanoes. In the interest of time, I won't go into that here, but we also have Fabien Albino later in the session who will tell us more about it. So how often do these volcanoes actually erupt? The historical record is very sparse and provides very little to no detail, so we have to rely almost entirely on geological evidence. This geological evidence can come from terrestrial sequences, for example pyroclastic deposits, which we can log and measure to understand eruption style and magnitude. However, lake sediments in lakes nearby volcanoes can often also preserve fine volcanic ash deposits that are not always preserved on land, and can thus provide vital additional information on eruption frequency, particularly for moderate-sized eruptions. And from these kinds of reconstructions, and where the data exists, such as here for Aluto volcano in Ethiopia, we generally find eruption recurrence rates on the order of a few hundred to 1,000 years for some of the most productive volcanoes in the rift. Now, one of the most exciting developments in recent years, I find, is that based on very detailed field mapping of deposits, textural studies of volcanic particles, remote sensing of volcano morphology, and integrating all this with information from rheological experiments, we're starting to get a better idea on how some of these rift volcanoes actually erupt. One eruptive style that seems to be typical for peralkaline rhyolite volcanoes, such as Aluto, is the formation of so-called pumice cones. Instead of generating full-blown Plinian eruptions, like we sometimes find at trachyte volcanoes, these pumice cones tend to generate moderate intensity but unsteady eruption columns that may collapse and form pyroclastic density currents. These proximal deposits, together with the fall deposits, gradually generate a cone-shaped landform that sometimes contains highly unusual particles, essentially pumiceous actinoliths like the one shown here at the bottom, which has a smooth outer skin and a highly vesicular interior. And these are particles that we don't know at any other type of volcanoes. Towards the end of the eruption, the cone is then often breached by a rhyolitic or obsidian lava flow, as you can also see from this high-resolution DEM. So the rhyolite flow is indicated in pink. So this kind of information, together with a sense of eruption frequency that we can reconstruct from terrestrial and lacustrine sequences, has recently been integrated into a probabilistic event tree model for Aluto volcano, and which is the first of its kind in East Africa. So I'll leave you with these two key points that I'd like you to take home from this brief introduction. First of all, there are about 100 volcanoes that could still erupt in East Africa, and some of them have moderate to intense explosive eruptions every few hundred to 1,000 years. Second, the melts in the East African rift are rich in volatiles and alkali elements, and this has important implications for their rheological behavior and may also lead to unusual eruption styles. Thank you very much for your attention.